We have questions about the homework, so go ahead and ask your questions.
I don't know which number it is, but it's the one where you're looking in a mirror. And I thought I was doing it right. Then to me, I got the answer wrong.
Who's looking in a mirror?
Lots of people. You're supposed to tell.
I'm not authorized to view this page. Chapter 25.
So it's a bunch of.
This one?
Nope.
Oh, it's like later down here, right? This one?
I
Yeah.
thought I was doing this right.
Can I be the one?
Huh?
Can I be the one?
You want to be the one to explain it?
Yeah. Wherever you look in the mirror, right? Can you see all the people on the bottom? Al, Lou, Fred. Can you see all the people?
Some of them. Not all.
You can see all of them. Why couldn't you see Al?
This would be out of your line of.
You're looking in the mirror.
Yeah.
Where are you?
You're Ed.
I'm Ed.
I was not.
Oh, who
See,
are?
them are the lines, and see, go up a little bit.
I was Bo.
You see Ed right there? Oh, you were Bo?
Yeah. Ed can see everyone.
Alright, so you wouldn't be able to see Al. Everyone else you would be able to see.
That's what I thought.
Except for Si.
Yeah. So why can you? Why are there
Because
certain
what you
people?
do is you take a straight line from your bow and you draw it to the.
To the corners, right? And then you.
No, you just draw it straight across to the letter. Right?
So if you-
Si is C, you would draw from bow to C. If you don't go through the plane of the mirror, you can't.
So you can do it two different ways. You can either use the law of reflection and go and do a reflection off the mirror to every point out here and see if you get a same angle. Because remember, you have to have the same angle, incident and reflected. Or the same thing goes geometrically if you draw a straight line through the mirror to the image points. And that's why they put the image points on either side. And so that's what he's saying, is that if you just draw a straight line and you actually go through the mirror, then you can see that person. If you don't go through the mirror, you don't see that person.
See, you wouldn't even be able to see yourself either. So you wouldn't be able to see Al, Bo, and Si.
Yeah, so Bo here can't see himself in the mirror, right? Can't see Al, can't see Si, but he can see Doofus, or whatever D is. Who's D? Nope, he can't see Doofus, right? Who's D? Die. But he can see Ed. He can see Fred. Can you see Fred? You can see Fred. Right? So that's one way to do it. The other way to do it is to draw a line. Is to do this thing. So let's say that I'm die. If I'm die, then I can draw a line from each of these guys, making a nice even angle. But that's actually much more difficult. So you have to have a compass, and you have to make all kinds of measurements. And it's not very easy to do it the standard way, which is why they put those images up there so you can do it an easier way.
No.
I thought that was a really good question.
I thought it was good. Number 12 is the one I had questions about.
Number 12, huh? So a ray of white light strikes the round side of a semicircular dish filled with carbon tetrachloride. Strikes.
1.461, I
Okay, that has an index of refraction of 1.461, apparently, right there. Okay. But that's only at the middle of the visible spectrum. For red, it changes by 0.5%, and for blue, It changes for 0.5% for violet and
So
red.
one is plus 0.5%, the other one is negative 0.5%.
That's right. Which one is which? That's the question. But anyway, the critical angle here is going to cause the blue light to reflect and the red light to refract, because the critical angle will be smaller for blue than it is for red. Right?
Yeah, but how do you figure out the critical angle?
So the critical angle is in the total internal reflection section. So if we go out here to 25, then we go to total internal reflection. Critical angle is defined when theta 2 equals 90. So when theta 2 equals 90, sine equals 1, sine of theta 2 equals 1, and then the equation becomes this, and your critical angle is theta 1. So you solve for theta 1 to be the critical angle, which is the inverse sine of n2 over n1. So critical angle depends on the index of refraction of both materials.
So it's 1 over 1.46.
Are we in air in our problem?
Yeah, you're going from air to...
No, we're going from tetrachloride to air, because we're inside the lens.
Oh, so it'd be 1.460 or arc sine of 1.460 divided by 1.
So it's for total internal reflection, it's the material that you're in, which is N1, is on the bottom. So the tetrachloride, so it's 1 over 1.46116, whatever it is. So for this one, critical angle is 1 over 1.461 plus or minus the 0.5%, because that's the thing we gotta. So we gotta take the plus 5% and the minus 5%. Oh no, it's for the first one. They want to know when it's going to occur for the middle of this. So this one you do for You do this one for 1.461 for the first one. So 1 over 1.461. Take the inverse sine. And then if the white line is shown at this critical angle, what is the angle of refraction at the red end of the spectrum? So we got to figure out which one is going to be red and which one's going to be blue. So which light bends more, red or blue? Turns out blue bends more.
Yeah, because it's number 3.
So that one's plus 5%. So blue is actually higher frequency,
So blue,
shorter wave.
1.461.
It's going to be 1.461 plus 0.5%. So you're going to have to take 0.5% of 1.461
So
and then add that.
1.461 times 1.05.
Yep. No, times 1.005, because it's 0.5%. So it's 1.005, and that will give you the index of refraction for blue, and then 0.995 times 1.461 will give you the critical angle for the red end of the spectrum. So that's this one. 0.995 times 1 is B, and 1.005 is C times the index of refraction.
I think I got the numbers figured out.
Did you do that one already, Patrick?
I know how to do all the ones there. I will
Okay, anybody else have any questions? Any other questions about homework? All right, well, that's Let's see here. Is there anything that we haven't covered in this chapter? I think we've covered everything in geometric optics.
Yeah. The only thing I'm gonna have to print it off is the positive and negative rule. Because I get confused on them and all these.
Oh yeah. In the image formation. Do you want me to go over that really quick, or do you want me?
Yeah, that would be great.
Okay. So when you're making images with lenses or mirrors, there are some rules about things. So for a focusing mirror and a focusing lens, the focal length is always positive. Okay, so for a focusing lens, that means that you have, essentially what it means is that your lens is thicker towards the middle and thinner towards the edge. So it can look like this, or it can be flat on one side and curved on one side. It can even be curved on both sides, but the middle needs to be thicker than the outside for it to be a focusing lens.
All right,
Okay.
and the positive and negative for in front or behind, depending on whether it's in front of the focal point or behind.
No. So let's just talk about focal points right now. Let's not talk about image distance and object distance. Just the focal point. If we're just talking about the focal point, for a focusing lens or a focusing mirror, the focal point F is a positive number always. So this is what a focusing lens looks like. It's thicker in the middle than it is on the edges. And for a focusing mirror looks like this. It is concave on the side that it is reflective. That's a focusing mirror. The focal point for each of those is considered a positive number. F is a positive value when you plug it into the equation. For an unfocusing or a non-focusing or a diverging mirror or lens, it's considered a negative distance. So F is always negative, and for a mirror, that means the focal point is behind the mirror. For a lens, it's not so obvious because it's just things, you could call it back focusing or something like that, but it's always behind the mirror. So, but for a lens, the lens is always skinnier in the middle and wider on the edges if it's a non-focusing or diverging lens. And that focal point is also negative. Okay? So that's just F. Now, when you're talking about distance to the object, the distance to the object is always positive. Okay? No matter what. Distance to the object is always positive. For a lens, the distance to the image is positive if the image is on the opposite side as the object. So if the object is on one side, the thing that you're making an image of, and the image is on the other side, then that is a positive image. And that's a real image. But if your image and your object are on the same side and you have to look through the lens to see it, then that's a negative distance to the image. Okay? So let me give you some examples of this. When we're making an image of the sun using a focusing lens, then the sun is over here and the image of the sun is down here. The image is on the opposite side of the lens as the sun, so it's a positive distance. Okay? When you're looking through your glasses, the thing I'm looking at is your face, which is on this side of my glasses, but the image that it's creating is also on this side. It's taking the object, which is your face, and creating an image that's closer to my eyes so that I can see it, but it's still on this side of my glasses. So in that case, the image is a negative image, and I have to look through my glasses to see it. With this, with the sun, you don't have to look through the magnifying glass to see the bright dot of the sun on the paper. You can look from the side and see it, right? But with my glasses, nobody can see the image I'm seeing unless they look through my glasses. So that's the only time you can see that image. That image isn't floating out here in front of my face somewhere. You have to look through the lenses to see it.
And that would be considered a real one.
That's it. The one that I'm seeing is a virtual image. A virtual image has a negative distance.
It's not actually where
That's right. A virtual image is not actually there. It just seems to be there when you're looking through the lens or the mirror. In this case, the image is actually there. It's burning a hole in the paper, right? So the image is actually there. You're actually creating an image that can be projected on the paper. That's a positive distance image, and that's a real image. Now, in a mirror, it gets a little confusing because you can create both of them in a mirror, but it's not as obvious sometimes. So, for example, we could burn a hole on paper using a focusing mirror. You'd get the sun there, and it'd be shining down, and you'd move that mirror so that the paper is at the focus of the mirror. And you can do that. That's how radar dishes work. A radar dish captures radar rays from space or whatever, or from air, and it focuses them to that little thing that's pointing out in front of the radar dish. That little thing is the receiver. So it focuses them to that point. That's a real image. And in that case, the object and the image are on the same side of the mirror. That's what a real image is for a mirror. So if your object and your image are on the same side for a mirror, it's a positive distance to the object. So if you're actually focusing light using a mirror onto some other object that's also in front of the mirror, then that's a real image. That's a positive distance for an image for a mirror. But most of the time when we look at mirrors, we're looking into the mirror to see the image, right? That's usually how we use a mirror. So if you look at a mirror and you see your image, or you see the image of a bottle or of a candle or something in the mirror, that is a virtual image. The image is behind the mirror. It's on the opposite side of the mirror than the object. And so that is a negative distance in the case of mirrors. So that's the difference between mirrors and in both cases, a virtual image, one that's not really there, is a negative distance. But with a mirror, it means it's behind, it's on the opposite side. With a lens, it means it's on the same side.
So whenever you do the math, it should tell you, right?
So if you're calculating for the distance to the image, you don't have to worry about it because the math will tell you what the sign is. But if you know the distance to the image and you're trying to calculate the focal length, for example, then you have to know which sign it's going to be, right? So there could be different situations.
So that's what every question I miss tells the sign.
Yeah, so if you pick the wrong sign for the focal point, for the focal length, that's a problem.
Like even magnification.
Yeah, so
Like some are graded in, others are making it small.
yeah, so if it's making it smaller, that just means that your magnification is less than 1. It doesn't mean it's negative. Negative magnification means the image is flipped upside down, it's inverted. That's what negative magnification means. And it means the distance to your image is either the distance to your image is negative or your focal length is negative. One of those two. There are a lot of possible negatives. Well, actually, it just means the distance to your image is negative. Yeah, because you can calculate your magnification with the two distances, right?
So the image to the distance to the mirror, if it's negative, that means the image is inverted.
Yeah, so you're going to get an inverted, let's see. No, that's not right. No, because magnification already has a negative sign on it, right? Sorry. So magnification, let's look at the formula for magnification really quick because I forgot there's a negative sign on it already. So if you're in, okay, so for magnification, it's really quite simple. If they give you the magnification, a negative magnification means that your image is inverted, but remember that the formula for magnification is negative distance to image over distance to object or something like that, right? There's a negative sign in the formula for magnification. That means that if you have a real image, if your image is a real image, it will always be inverted. Okay? So a real image is inverted. A Virtual image will always be upright. Right?
Alright, so negative magnification equals inverted, which equals a real image.
Yes, an inverted image will always be a real image. So if the image is upside down, it's a real image. If it's right side up, like when you're looking in a mirror, and you have a right side up in a flat mirror, that's a virtual image. If it's right side up. When it starts to, like if you look in that mirror in front of you, if you get close enough to it with your finger, for example, turn that mirror towards you. Actually, go the other way. No, turn it the other way. There we go. If you get close enough to it,
Yeah, see now I'm upside down.
yeah, once it starts flipping upside down, what you're actually creating is a real image at that point.
Yeah, exactly.
Yeah, you start to be able to see it above the mirror.
So most concave mirrors make a real image.
If you get close enough, you get closer to the mirror than the focal point. So if you get inside that radius divided by 2, then yeah. And so you can actually create a real image of an object. So let me show you this. Let me show you how we can do this really quick. It might freak you out a little bit. Ready for this? Sometimes you can get it to better with parabolic. Sometimes you can actually get that image just right so that you can see it right above the mirror. Can't quite see it. Can't see that. Sometimes you can get the image to float up there, but you do some close and slow.
I understand what you're saying.
But there, I keep needing to buy one of these
And
demonstrators.
that would be the one that you've seen would be a vertical.
The one that we can create that looks like it's floating above the mirror would actually be a real image.
It's a real without
And
convection.
it would be actually.
the same way that it was in
That's
there.
right. Well, no, the real image will be inverted. It will turn it upside down, right? So once you get your finger close enough, you get it. So these ones, let's see. So you get the right to focus on this paper. So
Yeah.
that's starting to focus on one. Here's the real image.
Okay. And that's a focal length more inside.
Yeah, for a convex mirror, you have to get it really close in. It has to be your image, your object actually should be at infinity for that, for what I was just doing, and then your image will be at the focal length if you do it that way. If you put your object in close, then you actually get the reverse thing happening. But the point is that if you have something that's upside down, if you're creating, let's see, let me think here. Your focal length is positive, and if your focal length is positive and your distance to your object, your image is positive, then you're going to get a negative magnification, which is inverted, right? So if you have an inverted image, then you can create a real image, is what the idea is. But if your magnification is negative or positive, that essentially tells you what that DO over DI is, because your distance to your object is always positive. That means if you have a negative magnification, your distance to your image is also positive. If you have a positive one, then that distance to the image is negative.
Yeah, because it's always DO over DI with your magnification.
Negative
It's
D over
negative
DI.
DO over DI.
Right.
So those numbers has to be negative.
Yep.
Like a positive.
So that will tell you whether your DI is positive or negative, which will also tell you whether your image is
Yeah,
real or
because if your
virtual.
If the distance is negative, then
Yeah.
magnification is positive. Magnification is positive, then it's virtual.
That's correct.
Yeah. That's all.
All right. It is confusing. There's no doubt about it. We don't really we have experience with optics, quite a bit of experience with optics in our everyday lives, but since we don't have a true understanding of what's going on with them, it's not intuitive to us. So this stuff is completely non-intuitive. And so we have to create an intuition for it. We have to revamp our intuition because our intuition is incorrect. Okay, so before we get too crazy, let's talk about schedule for tomorrow. Tomorrow there is Inter-High Day, but we will still have our optics lab. We'll just put you in the next room over so you can work on optics. So you can do the stuff with finish up the stuff that you've been doing. And then Thursday we will have class as normal in here, where you will probably just do some more optics lab. We'll probably do the eyeball lab on Thursday. Hopefully you'll get done with everything else
because
tomorrow.
in all the math in 26, how much I make with it.
Yeah, it is. So in chapter 26, when we start talking about optical instruments, one of the first things we're going to talk about is microscopes. I'm going to skip to microscopes and telescopes first so that you can understand how to do the lab with microscopes and telescopes. With microscopes, you're essentially doing this same mathematics except you're going to do it twice. So you have light coming in through the objective lens, which is the lens closest to the object you're trying to magnify, right? You have light coming into that lens and creating an image over here that is a real image. And it just so happens that you can use a real image as an object. We call it a virtual object. So if you use this real image as your object for the eyepiece and do the math again, and here they're doing it in ray tracing, then you can focus that image to a place that's on the same side as the object, so it's a virtual image, but it makes a huge virtual image so that you can focus on it and actually see detail. And this is one of the reasons that many people struggle to look through microscopes. Have you ever looked in a microscope and had a hard time seeing what's in there? Never? Never had to relax your eyes until you could see what's going on? If you're looking through a really high-power microscope, it's actually very common to have a difficult time seeing what's going on because most people assume that they're trying to look at something close to their eye. And so their eyes automatically try to look at something close. They try to focus on something close. But really the image is actually about 20 centimeters away, 25 centimeters away from their face. Their image is actually maybe even further away from their face than the end of the microscope. And so what you have to do is tell them to relax and try to look beyond the eyepiece, try to look deep into the microscope. The same thing happens with telescopes, especially on rifles, for example. On a rifle, people who look through a telescope on a rifle have a tendency to try to look far away at something. So their eyes are trying to look far away when really the image is, again, put at 25 centimeters from your face. People that are used to microscopes and telescopes have a tendency to not have to worry about it. They just automatically just relax their eyes and let their eyes, it's like reading distance is what you want to do. And so people who are nearsighted want to take off your glasses and relax your eyes and pretend like you're reading something 25 centimeters from your face. And then you'll be able to see everything just fine through a telescope or a microscope. So these things are these things are designed, both telescopes and microscopes, they're designed to do really the same thing. They're designed to take an object that is in a bad place for your eyes to focus on it and put it in a good place for your eyes to focus. Our eyes naturally focus at about 25 centimeters. And so for the microscope, it takes something that's very close and puts it a little further away and makes it really big. So you can focus on it very relaxed, and you can have a relaxed focusing distance, and you can have a big magnification so you can see detail. But this just uses that equation twice. It uses the lens equation twice. It uses the lens equation once for this image, and then it uses this image's distance to this lens to create this new image over here with this new magnification. So 2 magnifications, 2 image creations, 2 uses of the equation. To get the overall magnification, you take the magnification that you get from the objective lens equation and multiply it by the magnification of the eyepiece lens equation. Multiply those 2 magnifications together and you get the total magnification overall.
The only thing you have to do is whenever you do it, you have to organize your problem.
Yep. So let's take a look here. We have the object distance is given as 6.2 millimeters, and the image distance DI is not known. So this is object distance, DO. DI is not known. We're going to calculate that DI. So we just use the normal equation. In this case, we have a positive lens, so F is positive. DO is, of course, positive. DI is going to end up being positive 186 millimeters. The magnification from the first lens, from the objective lens, is going to be negative 30 according to that equation. Now, to do the second part of the lens, the second part of it, we calculate the distance to the eyepiece as DO prime. Right? The distance to the eyepiece turns out to be the distance between the objective and the eyepiece, which is 23 centimeters. Subtract off, let's see, the distance to the image. So the distance between the eyepiece is 230 centimeters. Subtract off, 230 millimeters. Subtract off the 186 millimeters, and you're going to get the distance to the object prime, or the second distance, which turns out to be 44 millimeters. So then with 44 millimeters and a 50 millimeter eyepiece lens, we can actually calculate now the distance to the overall image, which turns out to be this one right here, and you invert that to get 367 millimeters, so 36.7 centimeters distance to the image. So the magnification of the eyepiece is going to be calculated by DI over DO prime with a negative, and that's 8.33. So the overall magnification is the 30 to begin with, which is negative 30, and the 8.33, so it's negative 250. Notice that the first one, the first lens, the objective lens, the one that's close to the thing that you're trying to magnify, creates a real image, but the eyepiece creates a virtual image, right? And that's good because you're looking through the microscope. You want a virtual image. You're going to look through that lens to see it, right? There are microscopes that create real images. For example, a scanning electron microscope actually creates a real image of its waves. It doesn't use light waves, it uses matter waves. But it creates a real image on a screen. So in an electron microscope, you don't have to look through anything. You just look at a screen. So let's look how that works really quick. So here's how a scanning electron microscope works. You have these electrons that are coming down through here, and the electrons bounce off of the material essentially and onto a screen, onto some kind of device here that shows you what's going on. So the thing that you're looking at is this. It's usually a camera right here, but that is the idea. So it creates a real image of what's on your sample. Here's a better one here. So you have all these electrons that get focused down through here, and as they hit whatever the sample is, they come off here and get detected and go to a screen. Anyway. Okay, so that's a microscope, and a telescope is really the same kind of mathematics, but just a different situation. With a telescope, you have something coming from far away, so the light rays are coming in parallel to each other because it's infinitely far away, or very, very far away. And when you have stuff coming from very, very far away, it will focus, and then you can use another lens to focus an image onto your retina, or you could think of it as creating an image on the other side of the lens that you can focus on, something that's about 25 centimeters away from your eye. Both things actually happen with telescopes and microscopes. With a telescope and a microscope, you actually do get an image that focuses on your retina so that you can actually see it, so your eyeball can detect it. But whether or not that is being directly done or it's being done secondary from your final image, it doesn't really matter. But both things actually do happen. There are multiple images besides even just these two that are being created. So with a telescope, you can actually use a positive lens and a negative lens, or you can actually use two positive lenses, or you can actually use mirrors as well. So the telescope right there and the one behind you, they use a big focusing mirror on the back end, and then they use another, I don't think the second mirror is focusing, I think it's just a flat mirror, but a flat mirror to reflect it into a set of lenses that focuses it in. So that's a different type of telescope. The big difference between telescopes and microscopes and other things is that in some cases with a telescope, the object is so far away that you literally just have to put your distance to your object at infinity. And you do that usually when your distance to your object is like thousands of times bigger than your focal length. If it's thousands of times bigger than your focal length, then go ahead and just call it infinity. If it's not like hundreds or thousands times bigger, then plug in the number, it's probably going to matter. But once it starts to get to be thousands or millions times bigger, this 1 over distance to the object becomes so small it doesn't matter. It just becomes zero essentially, and your equation becomes this. 1 over your distance to your image is 1 over the focal length. Your image is going to be created at the focal length. And so in that case, the focal length of your objective needs to be at something that is going to do something with that image, because that is going to be where you're creating an image. So you put your eyepiece at that focal length, for example. You can put your focal length of your eyepiece at that length or something. So you can see that right here, that for something very, very far away, you have this image created by the objective lens here, and you put that thing really close to your focal length for your eyepiece, just inside the focal length for your eyepiece, so that you can create this image out here. For something that's not super far away, you can just put it right at the focal length of your eyepiece, or the inverse focal length of your eyepiece. But with telescopes, we don't generally look at the actual magnification, because the actual magnification is kind of weird, it's kind of funky. For example, if you're looking at Jupiter, how big is Jupiter? Okay, Jupiter is humongous, and the image that you're going to create is going to be much smaller than Jupiter. So you always have an image that is a magnification that is less than 1. So that less than 1 magnification starts not to mean so much. But what does mean something is the angular magnification, how big it seems to be inside your telescope. So when you look through the telescope without the optics, you just look through the tube, Jupiter looks tiny. But when you put the optics in, it angularly magnifies it to make it look like it fills the telescope much more. And so the angular magnification is a magnification of the angle across the what do they call it? The parallax across Jupiter. And that is calculated by taking the focal length of the objective divided by the focal length of the eyepiece and putting a negative in front of it. And that gives you the angular magnification of a telescope. Some telescopes even have lenses in them that turn your magnification right side up, so that you have an image that's always right side up. Do they do that with scopes on your rifle scopes? So rifle scopes actually have 3 lenses in them.
The more money you spend, the better they
Yeah, and generally what happens with most things that have optics in them, if you're spending more on the optics, what's really happening is they're just putting more lenses in to correct problems. And that's the next thing we're going to talk about. Lenses cause problems. In reality, if we could make all of our telescopes with mirrors, we would, but mirrored telescopes have their own problems, their own challenges. Mirrored telescopes require that you have usually more space to put them in. Like a telescope on a rifle would be way better if it was a mirrored telescope. But it would be huge. It would be really cumbersome. But mirrored telescopes it's much easier to make a mirror than it is to make a lens. And lenses have this problem that they have this thickness in the middle and this thinness on the edge. The thickness in the middle and the thinness on the edge create what we call aberrations, because the light has to travel a longer distance through the middle than it does through the edge, which means that the light on the edge gets ahead of the light in the middle, and it focuses it badly.
You see, that's like one of my favorite practice trips is the school rock ski, right?
Yep.
Which it's the one I just bought for Dad was $1,500.
Yep.
And it is so clear. The reason is because whenever they make the glass, they can make them like 99.7% lead free.
Yeah, so lead also causes problems in glass, so the quality of the glass is important, but even more important is actually this, what I'm going to tell you right now. And this is the thing that they're not telling you because they don't want to confuse you. But this is what they really do. So here is a lens that has aberrations. You have light coming in, and because of the thinness of the lens on the edge and the thickness of the lens here, and also the angle of the lens. See, that angle is so sharp there? You remember when you put light at an angle, what does it do? It splits it into colors. Well, the splitting into colors creates blurry images, creates bad images. But also, look, it focuses at 2 different places. At one place for the red and one place for the blue. So it has 2 different focal points, which means it makes a blurry image. That's what we call, we call this, what do they call this? They call this something aberration, chromatic aberration. Chromatic aberration is this fuzziness due to the color of the light splitting up. To fix that, they actually put in multiple lenses. So they call this multiplexing, or they call it compound lenses. So they put one lens right on top of the other lens, and they actually fuse them together, so that when the light goes through, it's actually going through almost much more flat, and it corrects that aberration so that it refocuses all those different colors together again at the same point. So that's one thing that they have to fix. The other thing is the thickness of the lens problem here, where the light focuses at different places. And this is called spherical aberrations or geometric aberrations. And they fix that they essentially fix that the same way by using these multiplex lenses, or these compound lenses. And those get really expensive. So if you buy an expensive camera, it's heavy. It's not heavy because they just made it out of metal. It's heavy because they've got multiple lenses in there made of glass. The same thing goes for your scope. Your heavier scopes tend to be the more expensive ones. The reason that they're heavy is not just because they made them out of heavier metal. It's because they're full of more and more of these glass
And
lenses.
see, I got a
They
night-
also put coatings on the lenses to help with this as
Yeah,
well.
see, and I have a night course, which is right there in the $1,500, $1,800 range.
Yep.
And then I have that Swarovski. Swarovski's clear, but the night course, whenever you adjust the parallax on it,
Uh-huh.
right, you can almost tell how far away it is by adjusting the parallax.
Yep.
Because the parallax, it does that focal distance.
Yeah. So parallax does adjust where this thing is focusing properly, so that it's focusing properly all along the lens. And to understand what parallax is, a good way to understand parallax is to imagine looking at something very, very far away, like a star. There's a star very, very far away, and the moon is in between us and the star. And as we move back and forth in our orbit around the sun, sometimes that star looks like it's on one side of the moon, and sometimes it looks like it's on the other side of the moon, which makes the star look like it's moving relative to the moon. But in reality, the star is moving much less. We're actually doing our moving. And so that's the idea of parallax, is that there's an angular movement as you move back and forth with things. And so as you move your eye inside of a scope, it makes it look like something's moving far away.
Not when they get a lot of money.
That's right. So you can actually adjust for that. You can adjust your optics so that you can adjust for that parallax, so that you can eliminate that parallax, and your object stays where it should be, so that you can actually make sure that you're aiming at what you're shooting at, right? So that, yeah. So if you have good optics, you can eliminate, and it doesn't take much to eliminate parallax. When you build your telescope in your lab tomorrow, you will be able to eliminate parallax. It'll show you how you do that, and you do that essentially just by adjusting the distance between the lenses. So it's just it's a very fine adjustment. So that's certainly something that you can do with lenses.
Yeah, because trust me, I was having a problem with that with some of the, whenever I go to shoot any distance, right? If I don't have the scope, using cheaper scopes, whenever you move your eye, with the crosshair will move on your target.
Yep.
To, like the scopes I have now, you can move your eye.
Right.
And it stays, the crosshair stays perfect.
Yep.
It doesn't matter where you're at.
And that's because you fine-tuned the parallax for that distance.
Right.
And that's exactly what you do. But parallax can be very useful too, though, because you can use parallax to determine, you can actually use parallax to measure how far away something is.
Yeah, and that's, we should go to the government.
Which gun range do you go to?
I usually shoot up beside the town because I don't have a membership to walk. I need a membership, but I don't have.
They're not expensive. It's
No,
like-
but it takes like a year and a half to become a member.
Does it? Well, I guess if you want to be a member and you know somebody out there, I think that you can be faster. You can go faster. You know anybody out there?
Yeah.
Because I think if you're sponsored,
Yeah, I have like 50 people that want to sponsor me.
yeah,
I'm just like, because I go out and shoot in a competition and I do well.
yeah.
Like I do it.
Well, that's the end of today. That takes us through. We haven't done the physics of the eye, but we'll talk about that Thursday. So tomorrow, work on labs here, and Thursday we'll be back.